All right, hello again and welcome everyone to the September webinar from the ALC BRT Center of Excellence. My name is Nicolae Duduta. I'm from EMBARC, the World Resources Institute in Washington, D.C., and I'll be the presenter today. I want to check again if everyone can hear me and if everyone can see my screen. You should see my first slide, which is the title slide, which is Traffic Safety on Bus Corridor. Can you just please type a message in the chat window just to let me know if you can see the screen and if you can hear me. Yes, okay, so people can hear me. All right. Let me first explain how we'll organize the webinar, and then I'll go into the presentation. We have about an hour, and I'll plan to present for about 35 minutes, after which we'll have questions. The way I've been instructed to do this is to keep everyone muted, because it seems to be the easiest way. And we'll open it up for questions after the presentation, and then I'll kindly ask that you type your questions in the chat window, and then I will read them out, because not everyone can see what others are typing, and then I'll answer the questions. So with that being said, I'll just go to full screen and start the presentation. So again, to give you a very brief background on myself, as I mentioned, I'm a transportation planner with EMBARC at the World Resources Institute here in Washington, D.C. I've been with EMBARC for about 3 years. And the topic of the presentation is traffic safety on bus corridors. So I'll be giving an overview of some of the research and the project work that we've been doing in this area here at EMBARC. It is a very broad topic. It's difficult to cover in only 1 hour. So what I will plan to do is give a fairly broad overview and focus on these 3 main themes that I've listed here on the screen. The first one being, what is the overall safety impact from implementing a BRT, a busway, or other type of bus system, which is the type of question that is important to address in the early stages of planning a new system, especially if making decisions on funding or carrying out a cost-benefit analysis. The second question that I'll address is, what are the factors that impact safety performance on a bus corridor? And I'll give some examples from crash frequency models and from some road safety audits and road safety inspections that we've done on BRTs. And finally, I'll address the question of how do safety countermeasures impact operational performance for a bus system. And this is to show that the way we address safety in our work at EMBARC is we try to have an integrated approach where we consider safety as part of the transportation planning process. So even though I will talk mainly about safety, I'll also deal with how this relates to issues like pedestrian accessibility, the operational performance of the BRT, travel times, and so on. And I'll try to use case studies as much as possible to address all of these different questions. And the case studies will reflect the type of work and the places where EMBARC is involved. So you'll see a lot of examples from Latin America and some examples from India and from Turkey. I'll start with the first question, which is, what is the overall safety impact from implementing a specific type of bus system? And the question is a bit difficult to answer because the safety impact doesn't only depend on the configuration of the new system. It also depends on what was there before. And I'll illustrate this with an example of what I consider to be a fairly typical BRT from the Latin American context, which is the Macrobus BRT in Guadalajara. And you have here an image that shows what the street looked like before the BRT was implemented. It was one of the major arterial streets in the city with quite a lot of traffic. Already some priority features for buses. It seems like there is a bus priority lane on the curbside, but with not very good enforcement and a lot of traffic and some fairly chaotic turning movements. Now you see a picture of what the new bus system looks like. This is the Macrobus BRT that was implemented in 2009 in Guadalajara. And just looking at the changes that happen on the street level, you would probably expect to see a positive safety impact. So I'll just point out a few things. There was a reduction in the number of lanes, of course, to accommodate the BRT infrastructure in the center. Pedestrian crossings are shorter because there's a new median that has to accommodate the stations. And of course, the existing buses and minibuses on the corridor were replaced with a single operating agency. So again, this is an opportunity, first of all, to eliminate competition for passengers among the different bus operators, but also to have centralized operations control and driver training and so on. So yes, we would expect to see a positive safety impact just from the changes that we can observe on the ground. And when we look at the actual data, we see that indeed there was a positive safety impact. What you see here is a graph of crash data that we received from the Transport Secretary for the state of Jalisco, where Guadalajara is located. And you see the black line on the graph, which shows citywide crashes that remain more or less constant before and after the implementation of this BRT. But the vertical bars, which show crashes on the corridor, you can see that they are going down after BRT implementation, and they remain at a fairly low level during the first 2 years of operation. So there was a clear positive safety impact there, and it was sustained for the first 2 years that the system was operating. And this is consistent with the types of impacts that we've been able to see in other similar BRTs in Latin America and around the world. And this table shows a very detailed safety impacts from BRTs in Mexico City, in Guadalajara, and in Bogota, also from Ahmedabad, and one example from Melbourne in Australia. You see that the systems in general are fairly similar in their configuration, but they tend to replace different things. So Bogota, for instance, at least in Avenida Caracas, was replacing an existing busway. Nevertheless, the impacts are generally relatively similar. There is a clear decrease in fatalities and injuries on all of these corridors, and generally also reduction in property damage crashes, with the exception of Metrobus Line 3 in Mexico City, where there was a slight increase in property damage crashes. So when we look at the overall impact, when we do an estimated weighted mean effect from implementing the BRT based on the data that we've seen so far, we see that the results are indeed fairly consistent, and we see about a 52% reduction in fatalities, about a 39% reduction in injuries, and a 33% reduction in all crashes. And these are all statistically significant at the 95% confidence interval. And we see this for Latin America. We see this more broadly for the developing world when we average the results from Latin America and from India. So it seems to be a pretty clear indication that the implementation of BRTs in these places where we have been able to collect before and after data has had a positive impact on safety. So this would indicate that it would be important to start factoring this into the decision-making process, and when doing cost-benefit analysis to account for these impacts as well. Now, it is also interesting for us to compare our findings with other findings from the literature, and most of the literature that we found on this topic is from the US, and interestingly enough, often it shows opposite results. You see, especially the bottom part of the table, shows various examples from the US where there has been an increase in crashes after implementing different types of bus priority features. Of course, you will notice that it's not the same type of features. The studies in the US have mostly looked at peak hour bus lanes, or lanes that are shared between buses and taxis, or shared bus and HOV lanes. But it is interesting that there are clear differences in the safety impact of different types of bus priority measures. And it's not just developing world versus the US, because we also have the example from Australia, which is right in the middle of the table, where there was also a positive impact, even though the types of measures that were implemented in Melbourne are fairly similar to the US. So this was interesting for us to notice, and it's a good transition to the second question that I'll try to address in this presentation, which is what are the factors that impact safety performance on the bus corridors. And through this question, we try to better understand why there were these different differences in safety performance. And we try to rely as much as possible on on data analysis to address this question. Of course, as most of you are surely aware, it is always a challenge to collect quality data in developing world cities. This is especially true of crash data because there's also an issue of confidentiality, and the data is usually owned by the police, and they're usually quite reluctant to share it. Nevertheless, we have been able to collect quite a few useful data sets, mostly in Latin America, and we were able to analyze them, and one of the tools that we've relied on the most is crash frequency models, which are one of the more common tools in safety analysis, and essentially they are statistical models that aim to explain differences in crash rates at different locations through variables such as traffic volume, street geometry, or land use. They typically use a Poisson or a negative binomial distribution. And one thing that is interesting about crash frequency models is that the same geometric characteristics, for example block sizes, will tend to have different impacts on crashes, different levels of severity. So what was important for us is to develop different models for different types of crashes. So we have pedestrian models and vehicle collision models, and we have fatal crash models and property damage crash models. I'm showing some examples here just to better illustrate what I meant by developing different models for different types of crashes. I know it's always somewhat difficult to read and interpret models on a PowerPoint, so I will go into more detail in the following slides and pull out some of the key findings and illustrate them. But what I wanted to show here is one of the most common problems that we've encountered, which is that always a key variable in any crash frequency model is traffic volume, because it is one of the key predictors of accident rates, but it's also a kind of data that's very difficult to get in some places, and we weren't always able to gain access to this type of data. Sometimes we were able to include it, as in this model, sometimes we were not, and it's a clear limitation in our data analysis, and something that I wanted to mention right at the beginning. Another example of how to develop different crash models for different crash types is the one that we've done in Mexico City, where we have one model for pedestrian crashes and one for vehicle collisions. Another thing that's interesting in this model, and I've circled it here in red, is that we've introduced some variables for different types of bus systems to see their impact on safety. One thing that is interesting in this table is, first of all, the finding on counterflow bus lanes, which are a fairly popular solution, especially in places like Mexico City, but we found in our analysis that they are a significant predictor of higher crash rates, so a definite safety risk. So based on this, we would not recommend counterflow bus lanes. The other finding that is interesting here is that the variable for the center lane BRT did not have a statistically significant impact on crashes. This is interesting because in the previous slides I'd shown that when we did our safety impact analysis, we found that there were positive impacts from implementing these different BRTs, and that these were statistically significant. So it's interesting to ask why in the crash frequency model the BRT variable will not be significant. And the answer that we would put forward to that question is that it's not the implementation of a specific bus system in itself that will have an impact on safety, but it is the way it is designed. And in the case of this BRT, it's the changes that need to be made to the street infrastructure to accommodate the BRT. So I'll illustrate this. This is a Metrobus Line 1 on Insurgentes in Mexico City. It's the same example from the previous, from the crash frequency model. And you can look at some of the changes that were made to the street, which also, according to the crash frequency model, contributed to the better safety record. One is that you have to remove mixed traffic lanes to accommodate the buses and the station infrastructure, and removal of lanes was significantly correlated with fewer crashes. There are left turn prohibitions on most intersections on these BRT corridors. This is mostly to give more green signal for time for the BRT, but it's also a positive safety countermeasure because left turns are a major risk factor. And then, of course, the presence of the central median itself is correlated with fewer vehicle collisions. And because there's a central median, crosswalks are much shorter because pedestrians no longer need to cross the entire street. And in this case, when we look at the model, shortening the crosswalk by 10 meters results in approximately 26% reduction in pedestrian crashes. So the takeaway for us from these crash frequency models is that the way the BRT corridor or busway corridor is designed has a huge impact on its safety performance, and we believe that this is what explains the difference in safety impacts that we've seen in the literature. Now, I'll go into more detail on some of our findings and pull out some examples from the data analysis. One thing that was interesting for us to look at is to compile information on all the fatalities that we had in our database to see which types of road users were more frequently involved in fatal crashes. This is the result. About 54% of them are pedestrians. This is fairly common on any urban road. It's not specific to any type of bus corridor. But what was interesting for us to note here is that there were no fatalities recorded for BRT passengers in the database. We know of fatalities to BRT passengers from evidence in other cities, but they would be less than 0.1% if put into this pie chart. So the takeaway here is that the safest place to be on a bus corridor is inside the bus, but the most dangerous place to be is when you walk to and from the station. So really this helped highlight the issue for us that safety on a bus corridor is primarily an issue of pedestrian safety. And the most common type of crash that we have observed on these bus corridors, the most common type of pedestrian crash, is when pedestrians run across the street in mid-block and get run over by vehicles. It's for any BRT agency, this is likely to be the most frequent type of collision involving BRT vehicles. And because pedestrians are vulnerable road users, it's most likely to be severe or fatal as well. One of the major risk factors here is block sizes, and that is correlated with traffic speeds. And what we found in our analysis, and this goes back to the idea of developing crash frequency models with different levels of crash severity, is that for every additional 10 meters between signalized intersections, there is a 2% decrease in all crashes because there are fewer conflicts with fewer intersections. But there is a 3% increase in severe crashes because speeds increase and because there's a higher incentive for pedestrians to jaywalk when the crosswalks are so far away. Now, large block sizes are a very common feature of Indian and Chinese cities, where you often have as much as 1 or 2 kilometers between signalized intersections. And if you're a pedestrian wanting to cross the street, if you want to follow the rules and walk to the nearest signalized crossing, simply crossing the street can take 1 or 2 kilometers. So very few people will actually do that. And as you can see in this image from the busway in Delhi, and from many similar images that we've seen from other systems, what you end up when you have large block sizes is a lot of pedestrians crossing in the block. It's not only a feature of cities in China or India. We've seen it in other places as well. Even in Latin America, where you usually have a much denser street network, what we see is that, especially as you move away from the city center, block sizes start to increase. And you have an example here from the southern part of Avenida Caracas in Bogota. And the typical scenario here is when the city expands and the street used to be a highway connecting 2 cities, and now with urban expansion it becomes a city street, but it's not usually retrofitted to reflect the new land uses around it. So you'll have situations like the one in the image where you see the street just stretching out into the horizon, and the nearest crosswalk is here. You can barely see there's a red signal, but very few people will actually walk that far to try to cross the street. And this issue of traffic speeds and block sizes can be even a bit more complex on BRTs, and this is an example from the Transoeste BRT on Avenida Las Americas in Rio de Janeiro. And what happens here is that sometimes traffic gets congested and you'll have a long queue, either because of congestion or simply because they're waiting at a red light. And then pedestrians will try to cross in mid-block, and they'll just run through the stopped cars And as you see in the picture, the danger here is that the BRT is arriving at a much faster speed. In this particular instance, this was, the pedestrian was fine, but this is one of the most common types of fatal crashes that they've had on Transoeste. So it highlights how important this issue of pedestrian crossing in mid-block is. Now, the issue of speed is a bit tricky because it's not enough to simply post a lower speed limit. You have here two examples. The one on the left is the same street as in the previous example. It's the Transoeste corridor in Rio. And the one on the right is the southern end of Avenida Caracas, where the Transmilenio buses operate in mixed traffic. And you see that one street has a 70 km/h speed limit, which is much too high for an urban area with crosswalks. And the street on the left has a speed limit that is much lower. It's 30 km/h, but in reality, traffic goes at the same speed on both roads because the road is straight and the design speed is much higher than 30 km/h. So the point I want to make with these two images is that speed limit signs by themselves are not effective, and that streets have to be designed for their desired speed. Now, one issue that's related with this is how do we get pedestrians across the street in mid-block, because I mentioned that this is one of the key safety issues. And I wanted to address the issue of pedestrian bridges because they tend to be a somewhat popular solution, especially on these sections with longer blocks. And the problem with pedestrian bridges is illustrated by this image from Metrobus Line 2 in Mexico City, is that pedestrians don't like to use them. And even if the bridge is right there, as in this image, pedestrians will cross under it. So that's why we don't consider it to be a safe solution, especially on urban arterials, which are relatively narrow, and when there's a high incentive for people to just run across the street. We've also included pedestrian bridges as a variable in our crash frequency models, and we've seen that on urban arterials, they have no statistically significant impact on pedestrian safety. So it's not, from this point of view, it's not a useful piece of infrastructure, mainly because it's not being used by pedestrians to cross the street. Now, pedestrian bridges are very effective on freeways, and we have here an example from the Metrobus corridor in Istanbul. And when you have a street that has this many lanes and much higher speeds, then people will use the bridge. And when we introduced it as a variable in the crash frequency model, bridges on expressways were strongly correlated with lower pedestrian crash frequencies. This isn't to say that it completely eliminates the problem, because when we looked at the crash data for this Metrobus BRT in Istanbul, we found that the most frequent type of fatal crash would still involve pedestrians running across the street. You may not think that pedestrians would run across the street as wide as this one, and we were a bit surprised to see it as well, but it does happen, and it was a common cause of crashes. So then the question is, what should we do on urban arterials to allow pedestrians to cross in mid-block? And we would argue that the best solution is to simply have a signalized mid-block crossing. And you have an example here from a street in Mexico City. And the point of this example is also to illustrate one of the common problems with mid-block crossings, which is that often drivers will not respect the red light if the only conflict is with pedestrians. And this will vary a lot from city to city, but especially in this case, in Mexico City, and that's why I'm using this example, it was very difficult for pedestrians to cross here because even when the light would turn red for vehicles, the traffic would not stop, they would keep on going. So essentially, there was no difference for a pedestrian crossing in mid-block or crossing at the signalized crosswalk. We did a road safety audit on this road because they were planning to introduce a new Metrobus line that would use this bus lane. And one of the recommendations here was that they should add traffic calming measures along with the mid-block crossing to slow down traffic. The recommendation was implemented, and you see an image on the right. There is a traffic there's a speed hump next to the crossing. It's probably not the best design for a speed hump, but I don't want to go into that much detail. What I would simply like to point out is that what this does is it doesn't make drivers obey the red light, of course. They would still, if there's no pedestrian and the light is red, they would still drive through the red light, but it makes them do so at a much lower speed. So if the light is green for pedestrians and pedestrians start crossing the road, then drivers are much more likely to stop for them. Now, this is a type of solution that we had road safety auditors from Denmark comment on, and they said that they would not recommend a traffic calming device like a speed hump and a traffic signal in the same location, because one or the other should be enough. But we found that in developing world cities, where there's a much lower compliance rate from drivers with traffic signals, this is the type of solution that that is needed to help pedestrians get safely across the street. And then the advantage of the speed hump is that it just, it's a general speed traffic calming device, so it lowers overall speeds on the corridor, which also improves safety. Now, I want to move on to the third question that I want to address in this presentation, which is how do safety countermeasures impact operational performance? And this is directly responding to concerns that we've received from BRT agency staff, because most of the recommendations that we propose for improving safety, and these are the ones that I've shown in the previous slides, have to do with reducing speed, either by specifically adding traffic calming measures or by adding more traffic signals to shorten block lengths. So the concern there was, the way one BRT agency staff member put it is, do we need to take the R out of BRT to make it safe? Will this reduce speeds to a level where you completely lose the travel time savings and all the other benefits of BRT? And we were able to address this specifically for the Transoeste BRT in Rio de Janeiro, where we were invited to carry out a road safety inspection on the corridor after it opened. And we started by looking at what the safety issues were. We proposed safety countermeasures, and then we were able to build a micro-simulation model to test the impact of these countermeasures on the operational performance of the BRT. Now, to give you a bit of background on the Transoeste BRT and on the safety issues that we found, it's a system that has pretty much the same safety problems as we found on many other BRTs in Latin America. They just tend to be magnified here because it is a very wide street. It is as wide as 90 meters in some places, which is probably the widest BRT corridor we've ever had to work with. And it's very, very difficult for pedestrians to get across. The speeds are very high. They are 80 kilometers an hour in the center lanes and 70 kilometers an hour in the side lanes. So that is a big safety concern. And there are very few opportunities to cross for pedestrians. So, of course, a lot of jaywalking and a lot of fatal crashes happen on the corridor because people are just running across the street where the traffic speeds are so high. I'll focus here on three safety recommendations that we selected because they would have potentially an impact on BRT operating speed. One was to reduce the speed of the BRT from 70 kilometers an hour, where it currently is, to 60 kilometers an hour, and to further reduce it to 30 kilometers an hour at stations. And this is because we had observed that the majority of pedestrian crashes tend to happen in the vicinity of stations. Not necessarily because stations are more dangerous, simply because more pedestrians try to cross them. And also because there are potentially some conflicts between buses as well, especially on a system like Transoeste, where you have local buses that stop at every station and express buses that will bypass some stations, and then there's some potential conflicts when the local buses merge back into the express lanes. Another recommendation we had was to add more mid-block signalized crossings. Right now we measured that on this corridor, the average length between signalized crossings was about 600 meters, which is about 6 times more than you would see in a typical urban center. So it's a quite long distance and not one that you'd expect pedestrians to walk in order to cross the street. And we also had recommendations for reducing pedestrian signal delay. And I'll explain through this example why that was important for Transoeste. They do have mid-block signalized crossings. They've especially added them in places where crashes had happened with pedestrians in the past, and they were trying to address this issue. So in itself, this is a good safety initiative, but the problem in this case is the configuration of the traffic signal. Here's a button-activated signal, as you can see in the image, and I have a diagram here that illustrates what happens when a pedestrian arrives and tries to cross the street. This is an aerial view of the corridor. As you can see, it is really, really wide. As I mentioned, it is at this location, it is about 90 meters. And of course, there isn't enough time to let it, give 90 seconds of green time for a pedestrian to cross the entire street. That would never happen. So it has to be done in stages. But the way the traffic signal is timed is quite poor. We timed it. We went and we pressed the button on one side, and then it took 1 minute and 22 seconds before it turned green. And the green phase was so short that we could only cross the first part of the first 3 lanes, and then we had to stop again. And then we pushed the second button to cross the second part of the street. And you can see where this is going. It's all of these start to add up. And when we crossed the entire street, we counted. It took us 8 minutes and 4 seconds to get to the other end. And of course, nobody's going to wait 8 minutes and 4 seconds to cross. So what ends up happening is people cross on red. And just to put this in context, the Highway Capacity Manual recommends keeping pedestrian delay under 30 seconds and ideally under 10 seconds. And here we have 8 minutes and 4 seconds. So this helps show you the magnitude of the problem. Now, I don't have time to go into the detail of the specific recommendations that we had for signal timing and for where to add crosswalks. I can provide more references at the end, or we can address this through the questions. But I just wanted to quickly give an overview of the results that we had from the simulation, because we've used the Embark BRT simulator, which is a micro-simulation tool specifically designed for BRT operations that was developed by Embark Brazil. And what we did is we first built a baseline model that replicates the way the corridor looks like today. And we looked at several indicators, one being operating speed for different types of services. As I mentioned, we have express buses and local buses. We looked at travel time, and we looked at speed variance and speed variability. And we started with the baseline model, and then we started introducing changes that directly reflected the safety countermeasures that we were proposing. So the first one was to slow the BRT down to 60 kilometers an hour. The second one was to add a 30 kilometer an hour limit at stations. And finally, the last scenario, which I call here complete, is the one where we also added more mid-block signalized crossings, and we adjusted signal timing so that pedestrians have lower delay. Now, there are a lot of numbers, and I know it's difficult to interpret tables in a PowerPoint, but the key takeaway for us is that there was, of course, a slight negative impact on the operating speed for the BRT. Right? The express service goes from 32 kilometers an hour in the baseline scenario to 29.6. But it's still above the 25 kilometer an hour benchmark, which I found in the literature that is generally considered to be the threshold for high-quality BRT operations. This, of course, directly translates to a slight increase in travel times. It's an additional 6 minutes terminal to terminal. And interestingly enough, there's a lower speed variability. So in a sense, because the speeds have been lowered, overall the bus frequency is better maintained. But my main point here is that these impacts are relatively minor, especially compared with the potential for significant safety improvements. Now, we don't have enough data to provide an estimate of the impact on crashes from implementing these different measures. But from what we've been able to see in the literature from similar interventions is we could have a reduction of up to 60% in severe crashes, especially at the main black spots. So what we're hoping to do with this is to give the BRT agency, in this case, the opportunity to make a very informed decision and know that they're able to drastically reduce crashes, and especially severe crashes on the corridor, with only a slight negative impact on operations. Now, I wanted to also show this graph, which is interesting for illustrating this relationship between safety and operating speed. And this is from a report on the Metrobus BRT, Metrobus Line 1 in Mexico City. And the dots on the graph are speed measurements on different sections of the corridor. And for those of you who are familiar with Line 1 of Metrobus BRT, with Avenida Insurgentes, on the horizontal axis, this goes from the north side of the corridor to the south side, and speed is plotted on the vertical axis. So this section is the northern part of Insurgentes, which is freeway coming from outside the city and entering the city and turning into an urban arterial. So it's one of those sections with very long blocks and relatively high speeds. Then the center is the downtown of Mexico City, around Reforma. And then this is the southern part of the corridor that goes south of the Periférico, and again has very long blocks and few signalized intersections. And then the black dots that you see overlaid on this graph are the main pedestrian black spots on the corridor. And the point of this graph is to highlight that the place where we have the pedestrian black spots are, as I mentioned in one of the earlier slides, is towards the urban periphery where you have the long blocks and the really high speeds. So these are the locations where we would recommend speed reductions and traffic calming. So this would not affect the most congested part of the city or the BRT corridor, but really would only affect the two extremities towards the periphery. This is the end of my presentation. I want to thank you for attending. And as I mentioned at the beginning, this was only a brief overview of the different aspects of our work, both research and projects, on the topic of safety on bus corridors. And for those of you who are interested, I know we can circulate the PowerPoint, and I wanted to point out two additional resources. One is our Safe Design Guidelines for BRT, which is published on our website, and I'm providing the link here, which really goes into detail to show all of the common crash types and the types of countermeasures that we've seen applied in different systems, and just some best practices recommendations for designing BRT corridors. And then there's a paper that we published in the Transportation Research Record that includes all of the crash frequency models that I've shown in this PowerPoint, and has a more detailed discussion on the methodology and the assumptions and the data collection and so on. So if you're interested in learning more on any of these topics, we will circulate the PowerPoint so you can take a look. I will open it up now for questions, and I'm looking through the chat window now to see what the questions are. Just as a reminder, the way I've been instructed to do this is I'll keep everyone muted because it's the easiest way to organize this. Please type up your questions in the chat window. I'll go through them. I will read them to the rest of the audience, and I'll answer them one by one. Now I have a first question from Dario, which is, in the case of Transoeste, is the speed reduction suggested on maximum speed? What is the impact on commercial speed and fleet requirements? At the end seems to be a choice between more buses, cost, or more people killed. That's a good question, Dario. It's on commercial speed. It's not. So the reduction that I mentioned as a recommendation, it's the reduction on maximum speed. But what we measured in the microsimulation model is commercial speed. So we looked at the impact on commercial speed. We did not look at fleet requirements, but that's a very good question. It's definitely something that we should add to this analysis, because, as you say, in the end, this could be presented as a choice between having more buses for the fleet or more fatalities on the corridor. Okay. If anyone else has a question, please type it, and I will read it to the audience, and then I'll answer it. Okay, 3 questions have come in simultaneously. I'll read all 3 of them and then I'll go through each one in detail. So presumably you're able to see them as well on the screen, but the fonts may be too small. Dario is asking, can you please summarize the key recommendations in the safe design guidelines? Stefan is asking, why do you think that the US safety values have been so different? And Alexandros Nikitas is asking, do you have any results referring to the safety of Chinese BRT schemes? I'll start with the last two because they're shorter, and I'll get to your question, Dario, at the end. Do we have any results the safety of Chinese BRT schemes? No, we do not. We have tried to get data from Chinese cities, but I mean it is very difficult to get access to any type of data in China, especially safety data. So we don't have any data on safety from any Chinese BRT yet, but we would be really interested to look at it, especially because China has these super blocks and high vehicle speeds, so it'd be interesting to see how the BRTs perform there. The second question was, why do you think that the US safety values have been so different? It's difficult to answer the question because those studies are a lot of them are from the 70s, one is from the 60s. It's very difficult to get access to the actual papers, so I don't know exactly which systems they've looked at. I don't know what type of analysis they've done. I've simply seen the results in this publication called the Handbook of Road Safety Measures, which is a meta-analysis of previous studies. I think that part of it is because the lanes are shared between buses and other vehicles. That could be why there is a potential safety problem. One thing we've noticed when looking at the crash data is that when other vehicles are allowed to use the bus lanes, there tend to be a lot of collisions between buses and these vehicles, mostly because, you know, if it's just buses, then their movements are very predictable. They tend to go at similar speeds and they tend to stop in the same places. Whereas these other vehicles will stop in unexpected locations to make turns. And we've seen this as a common crash scenario in places like in Rio, where you have some bus lanes that are dedicated bus lanes and some bus lanes that are shared with other vehicles. That could be part of it. I really don't have enough information to answer that question because I don't have access to those studies. Now going back to Dario's question on if I could summarize what are our key recommendations in our guidelines, I would say that there are a lot of very detailed recommendations, but what it really comes down to is managing speed and keeping roads narrow and intersections relatively simple. From all the crash data analysis that we've done, from what we've seen in the literature, these are the 3 key predictors of crashes: traffic speeds, conflicts, and street width. So it really is about just keeping the streets relatively narrow and keeping intersections very simple. We have an example in the book that shows 2 intersections on the same corridor. It is Metrobus Line 1 in Mexico City. The bus system itself is identical. The land use is identical in both cases. It's just one intersection is a very simple four-way junction. It's very tight. It has no left turns. And the other one is a complex intersection with a lot of turning movements and a very complicated signal configuration. And the second one is of course one of the major black spots, while the other one is one of the safer intersections. So really, it illustrates that just getting the design right can have a huge impact on safety. So a follow-up comment I see here from Alexander is that yes, I know it's extremely difficult to get Chinese data, so yes, I guess we can certainly echo that. So probably a solution there, and what we've done in other places where we can get access to data, or we do get access to data, but we're not sure of the quality, is to do a qualitative assessment. We've done road safety inspections on a lot of these BRTs, which essentially involves looking at whatever crash data we do get, but mostly observing the corridor, walking along, making observations on conflicts and potential safety issues, and we were able to identify a lot of problems to that as well. So you can get information on potential safety risks and countermeasures even without data. It's more of a qualitative assessment. And in fact, it was helpful for us, to give you an example from Mexico City, because we don't always learn everything from the data. And one example is that when we did an inspection on the BRT corridor in Mexico City, we noticed that there were a lot of conflicts between bicyclists and BRT vehicles, especially on streets that don't have bike lanes. Bicyclists will rather be in the bus lane than in the mixed traffic lanes because they perceive that to be safer. But when we spoke to staff from Metrobus, they had a lot of crashes between bicycles and BRT vehicles. So from the road safety inspection, we were able to learn that was indeed a safety concern. But that did not show up in the data because bicyclists are reported as pedestrians for some reason in the crash data set for Mexico City. So when we were just looking at the data, all we could see were crashes between buses and pedestrians. And it was doing this road safety inspection that we noticed that, in fact, that also included crashes with bicyclists. And from that, we came up with the recommendation that, especially in cities that have relatively large biking volumes, that it's really important to provide bike lanes on BRT corridors, because otherwise you run the risk of having the bicyclists in the bus lanes. And I know that some places have shared lanes for buses and bicycles, but typically BRTs are not designed that way, and what you have is really large buses going at relatively high speeds, so that's generally something that we would want to avoid. All right, if anyone else has a question, please type it into the chat window. Okay, in that case, if people don't have any other questions, what I can do is point out these two resources again, the guidelines which are available on our website, and this paper based on the safety analysis, which is actually available through the BRT Center of Excellence website. And I guess we can wrap this up if there are no more questions, unless Laurel, unless you want to make any announcements about the next webinar in the series, please let me know.
Hi, yeah, we haven't finalized the next webinar in the series, but we will send out an announcement about it.
Okay, and I believe, so this is being recorded, so I can share the recording with everyone, and I can also circulate the PowerPoint.
Great, yeah.
All right, so if nobody else has any other questions, then I guess thank you all for attending, and we will circulate the materials from this webinar in case you want to read more about this topic.
Thank you so much.
And thank you for inviting me, Laura.